Well, hello and good evening, everybody, and welcome to this Royal Meteorological Society event, virtual event. Obviously, during COVID, we've moved all our events online now, and in a minute, I'll be introducing our speaker for tonight, but I've just got a few slides to go through, just some basic administration before we get started. The first, if you're interested, we have a public outreach platform called the Weather Club. It's a website. It has lots of weather and climate information, lots of content on there, information about events relating to weather and climate, and opportunities to get involved in some citizen science events was one of those I guess we're going to talk about today as well. The second slide is about being a member of the RMetS Society, and so for those of you who aren't a member, I just would encourage you to take a look at membership, and it may be something that you're interested in, and there's a web link at the bottom of this slide, so do take a look and encourage you to join the Royal Meteorological Society if that's something that interests you. So for those of you who haven't been on Demio before, welcome. There's a few little kind of tips to get the most out of Demio. So the first thing to say is we have recommended browsers. So if anyone's struggling during the course of this presentation, I would recommend that you leave the meeting and click the link or copy the link into one of the 4 browsers that you can see on the slide here, and then rejoin, and that should correct any issues, any technical issues that you might have. You can also make the screen, the slides a little bit bigger yourself, so you can expand the screen by using the 2 diagonal arrows near the top of your Demio slide. You can close the chat, which is the arrow pointing to the right and the vertical bar, and that will make the presentation screen a little bit bigger to be able to see the slides. We have got time for questions at the end, and I would encourage you during the presentation to start adding your questions to the chat area, and then we'll take as many questions as we've got time for towards the end of this slot. So without further ado, I'm going to introduce Ed Hawkins, who's here to talk to us today about improving atmospheric reconstructions for historic extreme events. So Ed is a professor at the University of Reading. He works for NCAS. He's very much involved in climate science, climate change, looking at both past data, but also predictions for future data. And at the moment, he's very actively involved. We were just chatting before we came live. Very actively involved in the IPCC assessment with the 6th assessment report, AR6, which is definitely keeping him busy at the moment. But tonight we're talking about, I guess, unlocking some of these historical observations to help with climate predictions. So I'll hand over to Ed.
Thanks so much, Liz. It's a pleasure to be here talking to everybody. So yes, as Liz said, I'm going to talk a little bit about our work that we've been doing on understanding past extreme weather events. And there's lots of people to thank on this opening slide, but the most important one are the 20,000 volunteers that have contributed their time and effort to recovering lots and lots and lots of old weather observations. And I know a few of them are probably listening, and so this is very much a public thank you to all of those volunteers who have given up their spare time to contribute to our amazing projects, and we thank them a lot for giving up their time to do that. We'll see what they've managed to achieve a little bit later on. So to start, perhaps a little bit of context about what we're seeing in the UK and around the world. We're obviously seeing the UK and the globe warm. In the UK, we have temperature records, official temperature records going back to 1884 from the Met Office. And so far, we've seen a 1.5 degree rise or so over the UK in that time. And just a few hours ago, it was announced that 2020 was the second warmest year on record by lots of international agencies. So it's very much a sort of a current hot topic today, anyway, at least, that we're living in a warming world, and that has implications for our weather as well. But the other important thing about this temperature change, for example, over the UK, is that it's only thanks to lots of people in the past taking weather observations that we can produce an understanding of how things have changed. So back in the 1880s, people were recording temperature all across the UK, on a regular basis, and it's thanks to them for doing that we have these records, and also the fact that we've managed to turn those observations into digital data which we can analyze to enable us to produce a record of how things have changed. And so that the people who took the observations and the people who converted those observations into data we can use and understand are critical to this whole process of understanding our changing climate. And we're also very vulnerable as a society to the weather. You know, I have a couple of pictures here showing some examples of how we are vulnerable. Many of you will probably remember the UK, the windstorm in 1987, which blew down thousands, if not hundreds of thousands of trees across the country. And we've also seen over the last few years lots of flooding as well, causing misery for many, many people across the country. We are vulnerable to extreme weather, and when it happens, it causes a lot of damage and to a great many people. And so understanding those extremes is critically important. If we understand risk and how we might ensure that we're less vulnerable, we have to understand the range of things that might happen in our weather to enable us to better plan for the future, like building flood defenses or stronger buildings, for example. And so having a better understanding of extreme weather is critical to ensuring that we are less vulnerable to the weather as it changes over time, as well as the weather that we experience today. But of course, extreme events have happened in the past as well. There's a couple of old photographs here. You can't see the one behind very well, but that's in Watford in June 1903, where a road is flooded. And the near one is in Chobham in London in October 1903, which also flooded. And we're going to talk a lot about the weather in 1903 as an example of past extreme weather. There's a lot of very interesting weather that year in 1903, which we're going to talk a little bit about. But that's just an example of the weather that we've experienced in the past. So extreme weather's always happened, it will always happen in the future, but understanding the weather conditions that cause some of these damaging events is better. We need to do that to improve our understanding now of how we can adapt and make ourselves less vulnerable. Because some of the most intense events have actually happened in the past. So the picture of Chobham there, the flood in October 1903, that occurred during the wettest month we've ever experienced. October 1903 is still the wettest month that the UK's ever had. And also in 1903, we're going to talk a little bit about what's called the Great Storm, or the Ulysses Storm, which occurred at the end of February in 1903. And there's an old photograph here from Phoenix Park in Dublin, where thousands of trees were blown down overnight on the morning of the 27th of February 1903. And there's some rather bemused looking people there wondering how all these trees have come down overnight. So this storm was very damaging. It wasn't just in Dublin. There's a photograph here from Morecambe in the north west of the country, where one of the piers was very badly damaged and blown down again during the same storm in February 1903. So we know this was a very, very damaging storm, and we'd like to add it to our records of very intense storms, so that we might learn more about where storms travel over the UK, the damage they can cause. And of course, if a storm like this happened today, it would cause more damage because there's more infrastructure in the way of these storms now. And so we'd like to understand how this event might damage today's infrastructure, as well as understanding how it occurred in the past. So back in 1903, the Met Office were collecting observations in real time. All around the country, they had stationed weather stations and barometers and thermometers, and every day those observations were telegraphed back to London in each morning, and so the Met Office could keep track of what was happening to the weather each day. And so they received reports from all over the country, so that they could draw charts like this, the Synoptic Chart, each morning. And this is the Synoptic Chart drawn with the weather at 8 AM on the 27th of February 1903, and you can see a very, very deep low pressure over Scotland, bringing very, very heavy winds over Dublin and Morecambe and the other places in northern England where lots of damage occurred. So the Synoptic Chart is very consistent with the damage from the pictures that we've already seen. And so this was a very, very intense low pressure storm coming across the country. and it was around about 958 millibars or so low pressure in the Met Office Synoptic Chart. But what we can do today is try and reconstruct this event using our modern technology. So obviously back in 1903, they had pen and paper and the telegraph to transport information, and they would draw the charts by hand. Nowadays, we have much more complex technology. We have supercomputers, we have numerical weather models which forecast the weather every day for us now, and we have the observations that were taken back in the past. And so what we can do nowadays is build what's called a reanalysis, which essentially is using a weather forecast model and making weather forecasts in the past. So trying to predict the weather, but with the observations available in 1903, for example, but using modern day technology. So we're using the weather forecast models that are used on a regular basis every day, but taking them back in time and pretending that we are doing a weather forecast in 1903. And so from that process, we can build up a full picture of what was going on in the atmosphere back then in 1903. And it's obviously not as well represented as it is today, because we don't, there's no satellites data from 1903, and the data is much sparser. But we can do our best at trying to reconstruct the atmospheric circulation all the way back then, over 100 years ago. And if we do that complex process and try and reconstruct this particular storm in 1903, we don't see such a deep storm in our reanalysis as the Met Office thought at the time. It's not as intense, the winds aren't as strong. And you may ask, well, which one of these is right? And I think it's probably fair to say that the Met Office in 1903 are much closer to the truth than our current reanalysis. Because, as we'll see in a moment, we just don't have enough of observations to constrain the weather forecast that we're trying to run. And the winds represented in the reanalysis are just not strong enough to cause the damage that we see from the photographs. And so we have good evidence that we're not getting something right in our reanalysis. And that's because we just don't have all of the observations that were available to the Met Office in 1903 in our digital databases now. And so on this map, we see lots of yellow dots, and they represent single observations of atmospheric pressure or sea level pressure over Europe and the North Atlantic for this particular day in 1903. And what you can see is there's not a single observation over England or Wales, and there's very few observations over Scotland and Ireland, and there are a few ships out at sea taking observations that we have measurements from. But we can't expect, I don't think, to represent a very deep storm with just those very sparse observations. But the Met Office were able to do it at the time because they had the observations telegraphed to them from all of the stations around the country. But that data has not been transferred from the original pen and paper format that the Met Office had it in and filed away into digital data that we can use and analyse. Many of those observations are still sitting on paper, in the archives of the Met Office, and have never been looked at since in many cases. And so we haven't gone through this very laborious process of transforming that data into data that we can use and analyze to better understand these extreme events. And that's what we're going to talk about today, is trying to improve that situation. Can we do better than we are at the moment? And so we're going to go on a hunt for lots of old data, which will become new data. We want much more data to better reconstruct these extreme events. And we're going to start our search at a rather unusual location. We're going to start it at the top of a mountain. We're going to start it at the top of Ben Nevis, which is the highest point in the UK, at 1,345 meters above sea level. And you may wonder why we're starting at the top of the mountain. And the answer is because at this time, there was actually a weather observatory at Ben Nevis, at the summit of Ben Nevis. So these three meteorologists lived at the summit of Ben Nevis in a hut, which you can see the photograph of there, for 20 years between 1883 and 1904. And you can see the photographs there, the snow and the ice and the rime that's formed on their hut that they lived in. And you can see the photograph of them in the winter conditions. So they lived there all year round. They did have the occasional holiday, but essentially they lived in this hut for 20 years, taking hourly weather observations. So every single hour of every single day and every single night, one of them would step outside and take the observations and record them. So, at 2 a.m. on Christmas Day, one of them would be outside taking the hourly weather observations. And essentially, they wanted to do this to understand how the atmosphere was changing as you went higher and higher in the atmosphere. So they also had an observatory at sea level in the town of Fort William, which is very nearby. And so they had a detailed record at sea level and at the highest point in the UK to be able to compare what was going on in the atmosphere to understand how things were different at height compared to sea level. So that's what they were trying to achieve. And at this time of history, this was the era of great exploration as we're traveling off to the Antarctic and the Arctic and those famous explorers. And I think these gentlemen were exploring the atmosphere in many ways. They were living in pretty harsh conditions, isolated for the winter months, cut off from anyone, just taking these hourly weather observations for 20 years. It's an extraordinary achievement, and the conditions they went through were pretty horrific for the weather that they had to experience, and most of the time they were living inside a cloud. But their observations were faithfully recorded, and we have hourly observations of temperature, both dry bulb and wet bulb thermometer observations. We have observations from barometer, and we have rainfall observations every hour as well. And this is one of the pages that is from the published data logbooks that we have available to us. So this is the only format we have the observations in, or we did have until a couple of years ago. They were printed in very great detail on 2,000 pages in the Scottish archives. And so this is the source that we have the data in, and it's not been digitized. It's not been transformed into digital data, which we can use and analyze today. And as this is the barometer page from February 1903, I've highlighted the moment that this storm went nearby to Ben Nevis, and there was a recording of around about 810 millibar in our modern units. As the storm went close by. So we're obviously at 1,345 meters above sea level, so the pressure is very low, and they recorded 810 millibars at the summit. So what do we do with these 2,000 pages? How do we turn these images of this original data into data that we can use and understand and analyze? And that is where our amazing volunteers came in. So a couple of years ago, we launched a project called Weather Rescue, where we put all of these 2,000 pages on a website, and we asked for volunteers to come and help us transcribe those observations from the pages into digital data. And there are 1.5 million observations on these 2,000 pages, and 3,500 volunteers stepped forward to help us out. And in just 3 months, we had completed all and rescued all 1.5 million observations, which is an amazing achievement at the time. To essentially recover all this data from Ben Nevis and from Fort William, taken over 100 years ago for that 20-year period, and to realise the ambitions of those very dedicated observers who lived at the summit for that long time, to ensure that their data could now be used and analysed in a modern context. And there's not been any regular observations at Ben Nevis summit since the observatory closed in 1904. The conditions are such that our modern technology just doesn't work at the summit. We've tried, and the modern technology just fails because of the severe weather conditions. It needs someone living there to take these observations. So it really was a very dedicated mission that these meteorologists undertook. So here is an example of the data. Now we've turned it into something we can use. This is the dry bulb temperature for that 20-year period at Ben Nevis summit. So the temperature range for about -16 to +16. That was the maximum and minimum temperature roughly. And the average temperature at the summit was almost exactly 0 degrees. So that was the kind of average conditions they were living in. They were living at freezing with half the year warmer and half the year colder. Very extreme weather conditions that they were living through. And you obviously can see the annual cycle and the extremes, the ups and downs of the temperature that they had to experience. So we have similar data for rainfall, for the windiness at both sea level in Fort William and the Ben Nevis summit, which is open access for anyone to use and analyze however they want to. And we also have, of course, the atmospheric pressure data that was taken by both observatories in Ben Nevis and Fort William. And so you can see the variation in pressure observed at the summit and at sea level. And, you know, for example, if you look in 1903, that observation of 810 millibars, it certainly was nowhere near the lowest that they recorded. In their very first winter in 1884, they recorded about 790 millibar, maybe even lower than that at the summit, and nearly bottomed out their special barometer that they had built specially to take these very low pressure observations. So it was an extreme event in 1903, but there were certainly more extreme events that occurred even earlier in the record. But this is now one of the data points we can add to our map to enhance our estimate of this, our case study storm that we've been talking about. And it's a very, very detailed record from 1 or 2 locations, but we need a much wider area of data to cover the whole country if we're going to better reproduce this storm. And so after the volunteers had finished the Ben Nevis data rescue project, I asked them, you know, have you finished? Are you bored yet? And they happily said, no, we're not bored. We're loving this. We're really enjoying recovering all this data. Please give us something else to do. And so we turned to another source of data, which is known as the Daily Weather Report. So these are the observations that were telegraphed from around the country to the Met Office every day. And these are the original handwritten records that were recorded from the UK, but also in other places such as Scandinavia and France and Germany and Spain. They're all telegraphed to around Europe, collated in London and in Paris and in other places. But this is the British Daily Weather Report, which is recording a lot of British stations, but also other places as well. And so there are twice daily observations telegraphed to London, all faithfully recorded by hand on these sheets, which were then available to the public a few hours later. And so this is the scanned image of the Daily Weather Report from the day of the storm in 1903 with very low pressures. You can't see that on the image, but you know, they're very low pressures recorded in some parts of Scotland. And so there's a lot of data here, which we would like to turn into digital data, which we can use. And so our volunteers kept going, and we gave them these pages to transcribe the data from, and we recovered another 1.8 million sub-daily temperature, pressure and rainfall observations from about 70 locations around the UK and Europe. And again, now we have that data. It's now available for anyone to use and to analyze and to better reconstruct some of these past historical weather events. So thanks to all of these volunteers, our map of observations looks a lot better than it did before. So before we had, you know, scattered observations over Ireland and Scotland and a few ships. Now the black dots are the new observations that we've recovered from these various projects. And they're now covering large parts of the country, of the UK, so we can better reconstruct these past events. So we've got data from Ireland, from the UK, from France and from Spain and Germany and the Scandinavia as well. And so all this data is then available to better reconstruct those storms. And so I would have liked to show an animation, but this software doesn't allow me to show an animation. So this is a snapshot of our reanalysis for this storm in 1903. And so on the left, we have what the picture I showed originally, showing the storm which over Scotland in the morning of February the 27th, 1903. It's around about 966 millibar depth storm. It's obviously got some strong winds, but nowhere near strong enough to do the damage that we saw. And the blue colors show the rainfall. So this is a 3-hour rainfall rate. So we're seeing several millimeters of rain every 3 hours over the dark blue regions. So you can see the isobars in black, the rainfall in simulated rainfall in blue, and the winds there in the orange arrows. And on the right-hand side, you can see our brand new improved version of the simulation of this storm. So what we've done, we've gone back to this reanalysis system and we've added in all of the new grey dots. So if you compare the number of grey dots on the left and the right, you can see there's a lot more data now available over the UK and Ireland and other parts of Europe on this morning, which will help us better reconstruct the storm. And so we can go back and do another experiment with this reanalysis system add in our new information that's been rescued by our volunteers to improve our understanding of this particular storm. And so this is now our new chart to compare with the Synoptic Chart. And it's now a much deeper storm with much stronger winds over the Irish Sea, causing damage at Morecambe and Dublin, like we saw in those photographs. And so this is now a much better representation of that storm than we had available to us previously. You know, we can see it by eye. This is this chart is much more consistent with the damage that we know happened over the UK and over Ireland. And so the new data that's been rescued has improved our knowledge of the storm. And so now we can go think about, well, what damage would this storm do if it hit today and caused damage to our modern day infrastructure? We can now go back and use this as an extreme example for the type of storm which might happen again. You know, we get these very deep storms. We want to continually add to our number of deep storms that we have information about, so we can improve our knowledge. And again, this graphic just shows the wind speeds in our two versions of our reanalysis for this particular storm. These are the 6 a.m. winds. So the color shows the wind speed at 10 meters from the reanalysis. And we're seeing wind speeds at a high 20 to 25, 30 meters per second over the Irish Sea, which is what's done the damage at Morecambe and Dublin. And that's much higher than in the previous version. So our observations have improved the simulation of this storm. They're producing higher winds, which are consistent with the damage that we know occurred. And so we can be much more confident that we're faithfully reproducing this storm as it happened in real time. And this was such a severe storm that the Royal Meteorological Society commissioned a special report into the damage that it caused at the time. And so this is actually a map from 1903, where they'd put together the different places where damage had occurred. And you can see all the little symbols, the crosses and the pluses and the minuses, where structural damage had happened, or trees were blown down, or unfortunately there were lives lost at sea. And this damage map is now far more consistent with our map from our reanalysis of where the greatest damage occurred and where the greatest winds were experienced. And so everything is now much more consistent, and so we can have much more confidence in our understanding of this particular event, and therefore other events that we can find in the historical record that we can add these new observations to understanding. But we certainly haven't finished. We know of hundreds more stations where there were observations taken in 1903. There were barometers all over the country and all over Europe at the time, and a lot of those observations are also still in the Met Office archives on paper, and in the French archives on paper, and in the Irish archives on paper, and in archives all over Europe, still waiting to be found and catalogued and scanned and digitized and transcribed. And we also know that as hundreds of ships, the Royal Naval logbooks have hardly been touched for this period as well, and so that we can probably fill in lots of the gaps over the ocean with the Royal Navy and the other navies from around Europe as well. So most of the ships have not yet been scanned or even catalogued fully yet, and so this is a monumental task that we have to try and do if we're to try and fully understand our historical changes in weather and climate. And just to highlight another example from this very unusual weather year, 1903, there's a picture right at the beginning of the flooding in Watford. And so you can actually see the horse and cart going through the flooded streets of Watford in June 1903 because of a summer downpour. And again, you can see our observations of that a very extreme weather event show very, very heavy rain over large parts of southern England. And again, the original version of our reanalysis on the left-hand side had nowhere near enough rain to match our observations. It wasn't producing anywhere near the flood that we know occurred. And I hope to be able to update the middle map, but the simulation is still in the supercomputer in the USA, and it hasn't quite finished yet. So the middle one is a very early test simulation we did. But even that, with a few added observations, shows a much more consistent pattern with the observations, seeing heavier rainfall when we've added some of these additional constraints to better simulate the weather of that period. And And in a few weeks' time, I'll be able to update that map, and it will look a lot more like the observations, I'm sure, when we're adding in all of the information that's been rescued by our volunteers to better reconstruct the circulation, the atmospheric circulation around this other extreme event which occurred in the summer of 1903. But as we're talking about rainfall, I'm going to move on now a little bit to a new project that we've been running over the last year to rescue more rainfall observations from around the UK. And this is another big effort that our volunteers have contributed to over the COVID lockdown period. And so, as well as understanding the atmospheric circulation, we'd also like to have a better understanding of how much rain fell over the whole country, going back as far as we can to understand variations in our weather, any trends in rainfall, and understand how much rain has fallen during extremely wet and extremely dry months, so we can map out floods and droughts in much greater detail. And so at the moment we have rainfall series which go back to 1766, and that's all England and Wales average. So that kind of represents the average rainfall over England and Wales. So it's a very long record, it goes back a very long way, but it doesn't give us any spatial detail about where that rain fell. It's a broad average. It doesn't give us the detail necessary that we need if we're to understand particular floods, if we're to help water companies understand the range of possibilities for their particular water region, for example. And so to do that, we need a much more detailed data set covering the whole country at as a sort of finer scale as we can. And currently, the Met Office can produce these maps showing the rainfall falling across the country, going back to about 1862, which is in itself is an amazing achievement to be able to map out the rainfall that far back in time. And here are two example maps. One on the right from February last year, which is the wettest February on record. You may remember all of the storms which came across last February. And also the October 1903, which is still the wettest month ever experienced in the UK. And so we can map out the rainfall over those months in pretty good detail. The black dots on all of these maps are the observations where we have rainfall data. So February 2020 shows it has far more observations available for mapping out the rainfall then. But even over Scotland, actually, there are large gaps in our modern day weather station network. We don't have as many stations as we might like over Scotland and other parts of the country. There are still quite big gaps, and those gaps are larger in 1903. You can see large parts of the country which don't have much data in at all, and so we have to use various techniques to try and extrapolate over the regions we don't have data. But we would like to have more data to map out these variations in much greater detail with much greater confidence. So if we ask the Met Office, well, how many rainfall stations do you have available to you to make these maps? And if you ask them that question, this is the answer you get. There are around about 3.5 million monthly rainfall observations in their digital archives. In the 1970s or so, there are over 5,000 rainfall stations across the country, which they have data for, which is an amazingly dense network of rain gauges. Since the 1970s, it's dropped off, and we're now got about 2,500 rain gauges across the country now. So we certainly don't want it to go down much more than that if we're to maintain our estimates of how we map out the rainfall today. But also going further back, we see a rather strange situation in that before 1961, there are very, very few station data in the archives available to make these maps. So there's only a few hundred stations up to about 1960, whereas a few thousand after 1960. And so what's going on? Did we suddenly start measuring rainfall in 1961? So no, that's not the case. As you might imagine, before 1961, a lot of the data is still on paper in the archives of the Met Office. And so this is what those pages look like. This is one example from Reading, where I'm currently sitting. This is one page from what's called one of the 10-year rainfall sheets. And these were collated and curated originally by the British Rainfall Organisation, and they've been curated by the National Meteorological Archive for the last long time. So there are 66,000 of these sheets stored in the Met Office archives in Exeter. And each one of these sheets contains up to a decade of monthly rainfall amounts for a single location. So this is Reading Forbury Gardens weather station in the 1890s, and you can see one observation per, or an amount per month over that decade, as well as the annual total and the average for each month over that decade. And you have lots of interesting other information on this sheet. You have the latitude and longitude, you have the name of the observer, where it's situated, and some rather useful information at the bottom about exactly how far to various landmarks this weather gauge is situated. So for this particular sheet, we know exactly where the rainfall gauge was, and we know the rainfall amounts that were measured. But this data had never been transformed into digital data that we can analyze. And so to take 66,000 sheets like this and turn it into digital data is an enormous task. These sheets cover the period from 1677, when Richard Townley started measuring rainfall in Burnley, up to 1960. And this will fill a giant hole in the understanding that we have about past rainfall variations if we're able to turn this into digital data. So it's an enormous effort. All of those 66,000 pages were scanned in 2019, and the images were made openly available to anyone who wanted them. But to turn this data into usable data, we need to transcribe the values from those images into a computer. And computers are not able to do this automatically yet. You know, they can't take these images and read the handwriting. It's just too difficult a problem at the moment for a computer to solve. Even some of the type data is very, very difficult for a computer to read automatically. And so the manual approach is essentially the only way that currently we can do this. And some of the handwriting, this particular example isn't too bad, but some of the examples from other sheets are pretty bad. And you need to have quite a lot of experience of reading handwriting to interpret some of the numbers. And so it's certainly not something a computer can do by themselves. So it would take one person doing this. It would take them many years to transcribe all 66,000 sheets. There just isn't the resources to do that. So how do we go about rescuing this data to be able to map out past variations in rainfall with far greater precision? And again, we turn to our volunteers. And the timing of this particular project was rather fortuitous, I would say. So we launched a project called Rainfall Rescue last March the 26th, which was a couple of days after everyone went into COVID lockdown in the UK. And so a lot of people were at home. Many people were unable to work and with spare time. And so this was the right time where people were looking for something useful to do while stuck at home and not able to to work perhaps, or to do their normal pastimes. And so people had more spare time and they wanted to be useful during that spare time. And we were lucky enough to get some media publicity through the BBC, and we had 16,000 volunteers step forward, which is an enormous number of volunteers to help us transcribe these pages and turn them into digital data. So we set up the website and launched it, and we were quite frankly shocked and amazed at the response from the volunteers. It was a full-time job just to keep up with the volunteers as they were chewing their way through the sheets at a rapid rate. And in just 16 days, all 66,000 pages had been transcribed 4 times. So 4 different volunteers typed every single number and the location information, and the consensus between those volunteers was extraordinary. We only had 0.1 or 0.2% of the observations where there was disagreement with volunteers. So we were very, very confident about the data that we've recovered. And in total, there were 5.28 million measurements that were recovered in just 16 days. So in those 16 days, we've more than doubled the entire digital archive of the Met Office, which they've carefully collated over many years and decades. And I estimate there's probably about 15 person years of effort which have gone into, which the volunteers have given to allow us to achieve that objective. And so if we now look at our graph of how many rainfall stations are now going to be available to the Met Office to improve their reconstructions. So in total, there were several thousand 10-year rainfall sheets covering a large period from about 1900 up to about 1960. So that again, this matches the available data, the available amount of data available after 1960. There's probably more stations available now before that period. But there's also a little wrinkle here in that we have to try and link together the different sheets. So I showed you a sheet from Reading Forbury Gardens from one decade, and we have to match that with the data from the other decades to produce the very long time series records that we would like to be able to pass to the Met Office to produce their reconstructions. We need to identify where the rain gauge was as precisely as we can, and put together the different decades to produce the long series that we need. And a small group of very dedicated volunteers have been helping out over the last few months with that task. We now have about 2,000 stations available. For example, at the peak period in the 1900s, there's about 5,000 locations overall that have different segments of the data that are now available. And so we've increased the number of stations available enormously. And we're still adding data every week. So the volunteers are still working very hard and committing a lot of spare time, and we thank them for that, to piece together these records and do the quality control, so that we can then improve our reconstructions. And so that's the black line, is the amount of data that we have now that we're able to pass to the Met Office, which they're already using to improve their knowledge of past rainfall variations. And so it's very much a collaborative project from the volunteers all the way through to the people producing the data sets and making it openly and publicly available for anyone to use the data. And I think that's an important aspect of what we're doing. So where is this data that we have available to us? So here are some maps now showing where the stations have been completed over the UK and over Ireland. So I've got 3 particular years here, 1836, 46 and 56. To show how the number of rainfall sites have increased over that period. So before, if you remember, the Met Office series started in 1862. They had nothing in their gridded data set before 1862. And so all of this data is new, and it will be able to then extend backwards in time those very detailed reconstructions of rainfall, probably back to 1836. Before 1836, we start to run out of rainfall observations in Wales and in Northern Ireland, and so it's very difficult to produce a whole UK series before about 1836. So 1836 is probably as far back as we can go in terms of reconstructing the whole of the UK, and the coverage is pretty good. As I said, we're continuing to improve this coverage all the time as we piece together more of these long rainfall stations. There are still quite large gaps, particularly over Wales and parts of Scotland, where there were probably no rain gauges at the time. There was probably no measurements taken, and obviously we can't travel back in time and take any observations, so we have to live with the data that we have available to us. But at least now we have available to us everything that was taken, and so we can do the best effort that we can to improve our understanding. If we look a little bit further forward in time to the 1880s and 90s and early part of the 20th century, we have very, very complete maps of where there were rain gauges, and now we have the data available to us. And this has improved the coverage enormously from what was available before over the UK, over Ireland, particularly over Scotland, where we now have a really good coverage compared to what was available before. There are still some gaps which we're working on filling, but this is a drastic improvement of what was available before, and it's all thanks to the efforts of our volunteers. And this means we can now map out some very extreme months in far greater detail than we could before, with far greater confidence. And so these are some very wet months. So we have November 1852, which wasn't mapped out before, but now we can produce this map of the very, very heavy rainfall that occurred in November 1852. And we can again map out the wettest month ever, October 1903, in much greater detail with far greater confidence than we could before. And we can also look at drought months. We can look at May 1844, again, which hasn't been mapped before, but now we can map out where the rain didn't fall in May 1844. and one of the various driest months that we've had in February 1932, again, we can map out with far greater precision and far more confidence than we could before. And so now this data is becoming available, we can go back, and water companies can think about how they would deal with situations where we had some very dry winters, for example, in the 1880s and 1890s, or some of these very dry months, or how would they deal with some of the floods that we know occurred in the past. How would they manage that amount of water if it fell today? Because a lot of the records are still in the past. So a lot of the record events are still in the past, and now we've got far greater confidence in those records. And so we can also produce very long time series of the UK average rainfall going back now to 1836. So we can extend our records further back in time, have better understanding of the long-term trends in rainfall. We see a trend towards wetter winters over the last couple of 100 years, which we think is partly due to our warming planet. We can't see such a big trend in summer, but we see lots of very interesting variations in summer rainfall and winter rainfall and autumn rainfall, which we're just starting to exploring all of those interesting variations and understanding the very extreme weather that has occurred in the past. So there are enormous archives of undigitized meteorological data. There's probably several billion observations worldwide, certainly several 100 million and maybe 1 billion observations just for the UK that have yet to be transformed from paper to digital format. And we can use the data to improve our understanding of past weather events, long-term trends, storms and floods, and improve our reconstructions of the past. And we've had many thousands of volunteer citizen scientists who have helped us do this, and it would not be possible without them. And so far, they've recovered around about 10 million historical observations to add to our knowledge, which is an amazing achievement. But we need to go faster. We need to speed up the scanning of those logbooks which are still in the archives, and some of them, unfortunately, are at risk of being lost. So we need to ensure that doesn't happen, and so we're working on that aspect as well. And if you want to help, there are currently 2 climate-related projects running on the Zooniverse, which is the volunteer citizen science platform that we use. So if you want to help some other teams who are currently rescuing sea level data, for example, from the UK, there's a sea level rise data project which is currently running on the Zooniverse. And there's also another project running with some US collaborators who are exploring ship logs from the Second World War. So if you want to relive the meteorological observations taken during the attack on Pearl Harbor, or when several US ships got caught in Typhoon Cobra with amazingly strong winds and amazing pressure observations, then those pages are now online for you to explore. So anyone who wants to help, visit the Zooniverse and find the climate projects that you want to get involved with. So please get involved if you can, and thank you very much for listening.
Thanks, Ed, and a big round of applause from me, and I'm sure from everybody else who's listening in. I was watching the chat, lots of people both saying very interesting talk, and a big thank you to all those volunteers who have helped out. But we'll move now on to the Q&A. We've got quite a few questions actually in the chat, but if you've got any further questions, please do add them to the Q&A, and we'll try and get through as many as we can in the time that we've got left. So the first question we've got here is from William. With the number of observations recovered by thousands of volunteers, how do you account for the possibility of any errors, and how does that affect the certainty of the reanalysis? I think you touched on this a little bit, Ed, but maybe you want to go into that.
Yeah. No, it's a very good question. And yes, I touched on this a little bit, but yes, we certainly always ask for several volunteers to independently transcribe every number. You know, people make mistakes, that's inevitable, and so we have a clear understanding that happens. And so for our projects, we've used various numbers of people doing every of the different values. When they've been typeset, we've actually used fewer volunteers per number because they're easier to read. When they're handwritten, it's much harder, and so we've actually asked for a few more repeats of each number. But with 3, 4, or 5 volunteers, we can normally be very, very confident that if 3 or 4 out of those 5 or 3 out of 4 have agreed on the number, then we're very confident that we can accept that value as being what is written. Of course, we can't account for observations that were miswritten or mistaken. You know, barometers are not always easy to read if you're, or rainfall gauges are not always easy to read, and so there will be inevitable errors in the original observations which we can't deal with. But that's true. That's true now and in the past as well. But also on a lot of the pages, not always, but sometimes you notice that there were averages. So there was an annual average or a monthly average. So the average of lots of the observations that we asked for. And so that adds an extra cross-check. And so if we look at all of the individual values and we're confident in those values, it should add up to the value at the bottom of the page, which is the average of that particular year. And in the vast majority of cases, that is the case. And so we've got this extra cross-check on the values, which makes us even more confident about the data that we've got.
Great, thanks. So I've got a couple of questions relating to the actual storm in February 1903. This first one, I guess they both questions actually relate to the amount of detail that you're getting from the observations now. So this one is about the return period. Is there any way, looking at this, you've got a feel of the return period of that kind of storm?
That's very difficult. We probably don't have the answer to that yet. It's something we would like to do. There are not many, of these storms in the past which have caused a lot of damage. There's that much damage. We certainly know of, maybe 10, 20, for example, over Europe that have caused this much damage, maybe a few more. And so, yeah, it's very difficult to come up with the return period number, but it's certainly, in the top 10, 20, 30 storms that have occurred over the last 100 or so years. So hopefully that helps a little bit answer the question. But yeah, it's a difficult one to answer precisely, I think. And
then related to that, so this storm again, is there any way from kind of the reanalysis, so actually look at the model that we can actually, for this example anyway, was there a sting jet involved that maybe had an effect?
Yeah, I would love to be able to answer that question. That's a really, really good one. And it's something I've been thinking about, whether we can do this. So the reanalysis probably isn't at a high enough resolution to resolve a sting jet. The reanalysis is done at about a 70-kilometer resolution, which is pretty good, but it's not a modern weather forecast model resolution. It's not the 1.5 kilometer, which we have over the UK at the moment, for example. And we can't run at a high enough resolution yet, because the supercomputer power needed is just orders of magnitude larger than what we have available to us. But there has been a lot of work recently from people in Reading, actually, about trying to diagnose sting jets from other things in the reanalysis. Even if you can't resolve it explicitly, can you see the indicators that are present when there is a sting jet? And so that is something we would like to do, is see if we can understand where those precursors and where those indicators of likelihood of a sting jet is present. And so we'd love to be able to answer that question. Yeah, it's a really good one.
So a couple of questions relating to the rainfall. So there's one, you showed a graph where we see a drop off in the number of rain gauges being used since the 1970s. And again, a question about why that's happened. And even though I guess more recently there's been a lot more amateur observers taking rainfall, those used, can those be taken into some of the more recent data as well? So why did we see that drop off in the 1970s onwards?
I think, partly it's resources, partly it is probably people unfortunately passing away. And many of these stations are actually run still by volunteers, volunteer observers. There's a large number which are volunteer observers and a large number which are official stations. So the number of volunteer sites, the official volunteer sites, has dropped off. But as you said, there are many more amateur volunteers who use, easily purchasable equipment, which could contribute. And so it's certainly true that the Environment Agency they would like to have interest from people who would like to be an official observing site. It's not, it's an intensive task. You have to take observations every single day, and your site has to be approved that it's far enough away from any obstructions, that it's a high quality rain gauge, and so on. But if you did want to volunteer to be an official observing site, there is a process you can go through, and they are always looking for volunteers over England, Wales and Scotland. So we would like to increase those numbers, but it would, it requires an inspection of the site and ensuring the rain gauge is high enough quality and that you're available to do it every day to enable that to happen. And so yeah, we don't want to have any more drop off. It's probably the case though, the observations that are available are very well spread out. So there's certainly very strong efforts to fill in large gaps. And so there aren't enormous gaps in the network, even with though there are fewer stations in total.
Right.
So yeah.
And this relates to your answer a little bit here, but rainfall data analysis is kind of correlated with the exposure of the rain gauge. And I think you did show the example of the observation from Reading Forbury Gardens, and it had the little bit of text at the bottom. So how would you actually kind of throw data out where you feel that maybe the rainfall data is not useful enough because of the site, the exposure of the rain gauge, or are you happy to take everything in, warts and all?
Yeah, that's another very good question. So, so a lot of the sheets do have some information about if there is any buildings or trees relatively close by. So some of that information is available on the sheets. At the moment, we've basically taken everything, or nearly everything. So the benefit of having as many stations as possible, even if they're very close by to each other, is that they might have different exposures. Or better exposures. So having observations very, very close to each other allows us again to do those cross checks between different gauges to see whether any of them are reading too low or too high. So having as much data as possible is very useful for those extra checks that we can do. We have independent evidence from other ways of calculating rainfall from the reanalysis, for example, and we've done a little bit of work comparing the reanalysis with the in situ observations, and over the regional averages they agree remarkably well. So I think we can be very confident in the regional averages that we're producing for the rainfall going back to to the early 1800s. There are definitely some weird observations from some of the early sites. There's clear inconsistencies, and so some of that data will eventually be thrown away, I think, because it just doesn't look physical. But it's another very good question.
So there's a couple of questions relating to Ben Nevis observations, and there's one that's got rainfall related, I guess. So let's start with that one. So obviously in the wintertime there's lots of snow falling on Ben Nevis. How was that converted into rainfall amounts for the observations?
So as far as I understand it, and actually there may be someone on the call who can answer this better than I can, but as far as I understand it, they took the rain gauge inside and replaced it every hour. So they melted the snow to record the rain depths and left the other gauge out there to record the next hour. That's my understanding. Stephen, if he's around, may be able to answer that better in the chat.
Great, thanks for that. And then also relating to Ben Nevis, this you mentioned we haven't had any observations taken since the early 1900s. Is there a reason why the conditions are so bad to prevent automated observations or observations being taken there?
Yeah, so when we did the rescue project, we actually, or I didn't, unfortunately I was unavailable, but a team carried up a modern set of instruments with solar panels and an anemometer and a wind vane, and sorry, wind power. So to try and see how long it would record for. This was in November, and it lasted 24 hours before it failed. And it's essentially the humidity, I think, which is the biggest problem. It's obviously extremely cold and extremely windy, but they have an automatic station on Everest, for example, and that works okay. So it's the combination of the high humidity, the cold temperatures, and the windiness, which causes enormous problems for the batteries in particular, and icing up the instruments. So yeah, it's a whole combination of factors. There has been talk about putting a really sort of even powered, we can't get power there, but we'd have to power it by some very clever technology, which isn't batteries. But it's quite a big task, and we're not sure actually that we'd want to build at the structure at the summit. It's a pristine environment, so there's all kinds of other issues that we would need to tackle before we went ahead and did something like that.
Really interesting. So this is a comment rather than a question, but for info, you may be aware anyway, Ed, but I wasn't. So at NOAA and National Severe Storms Laboratory in the US, in combination with a number of universities, you can see listed here, they've been experimenting using 20th century reanalysis version 3 to drive convection, allowing models to simulate 19th century tornadoes. It's not perfect, but you can see some tornadic storms. There's one from 1884. They've got as far back as 1875, trying to look at August 1814, when there was a tornado that hit the British encampment the day after the White House was burned. So there's obviously some interesting work looking at data in the US as well. And there was a little bit of chat in the between a few people asking about how is this data available. And so again, I think Harold's going to be in contact with somebody else about this. So, yeah.
Fantastic. Yeah, I mean, you know, we would also like to do something similar over the UK. You know, drive a higher resolution regional model over the UK with the 20th century analysis. That's something that, again, we've thought about but haven't yet got around to doing. I think we've been waiting essentially to ensure that we've got the best representation of the events possible before going the next step of trying to do the downscaling. But it's definitely something we'd love to do.
So I'll finish, and it's just really a plug. So this is a question saying, I'm a PhD student and I'd really like to be a volunteer. How can I go about it? So do you want to give one last plug to the website?
Yeah, so as I said, there's at least two projects running at the moment on zooniverse.org, which are weather or climate related. So one is the US World War II ship logbooks, and one is tide gauge data from Liverpool, so better reconstruct sea level rise around Liverpool. So those two projects are running there, but there are also lots of logbooks available which have all been scanned, which we need to digitize manually. So there's plenty of PhD projects in some of the archive images that we have already. You know, for example, we are trying to create a very long record from Exeter. There's data in Exeter going back to 1755, and there's a continuous record from about 1814 up to present, which hasn't yet been digitized. But again, that would be a single site covering a 200-year period nearly. So, you know, there's plenty to be done even now to try and recover some of this old data.
Great. Well, big thank you, Ed. And I know some of the volunteers that have already helped out were on the watching the talk, and I'm sure there are others who will help with future volunteering as well. So big thank you from me and everybody else. I can see some kind of virtual rounds of applause going on in the chat. So I've just got a couple of slides. So, you know, if you want to keep in touch, I think the presentation from tonight will be put up on the RMetS Society's website in the next few days for delegates to watch again and for others to share who haven't been able to make it today. And then my final slide is just a couple of presentations that are coming up in the next few weeks. So, as I say, virtual meetings at the moment because of COVID, but we've got the Yorkshire Local Centre meeting on Tuesday, the 26th of January. And then the South East Local Centre have got a virtual meeting on Tuesday, the 2nd of February. You can see the dates there. So hopefully you can join either or both of those virtual meetings. So all I can say really is a big thank you again to Ed. Thank you to everybody for joining, and particularly those who are volunteers. Thank you for all your input. Fantastic work, and great to see it's being put to some excellent use. So all I've left to say really is bye from me and bye from Ed.
Thanks so much, everyone.